All right, guys, we're going to finally talk about how to find area under a curve in a more streamlined manner. So this is a technique that we will be using for the rest of this calculus course. So this is a super important lesson for you. Basically, no more making rectangles to estimate area under a curve. I'm going to show you today how you can find the exact area of a curve under a curve using anti-differentiation. All right, so the name of the game is called the evaluation theorem. So our job is to find the area under a curve from point A to point B, and here's the name of the function. What you will do is you will first compute an antiderivative. Okay, so remember, capital F represents antiderivative. Once you compute that antiderivative for the function given, you will plug in the b value to the antiderivative. You will plug the a value into the antiderivative, and you will subtract, and voila, you will have the area under the curve. It is that simple. So let me show you how all the work will look here. So the first step to evaluate from 1 to 3 would be to find the antiderivative of e to the x, which we already know is e to the x. So once I have my antiderivative, I will remove this symbol and replace it with a bracket where I will put a 1 and a 3. And that 1 and 3 there at the end of the bracket are going to remind me that I need to plug those values in to evaluate my integral. So the next thing you do is you have your antiderivative. You're going to plug in the b value first, so that's the top number. And you're plugging that in for the x. And then you would subtract and then plug in the a value, and you would get e to the third minus e to the first. And then you would simplify if possible. There's not much simplifying that can happen here other than making e to the first just an e. So this, if I were to compute this numerically, that would be equal to the area under the curve of e to the x from point 1 on the x-axis to 3. Okay, example 2, find the area under the cosine curve. So that means find the area under the cosine curve from 0 to pi by 2. Okay, so what you would do is you would do your antiderivative first. Oh, not 0 to pi by 2. Goodness, sorry, 0 to b it says. 0 to b says it right there. Okay, so do your antiderivative first for cosine. The antiderivative of cosine is the derivative of what gives you cosine. That would be sine. And then we will plug in the top number first and the bottom number second. So that would be sine of b minus sine of 0. And then evaluate where you can. Sine of 0 is equal to 0. So if we simplify this all the way down, we end up getting that sine of b would be your solution. Basically, this seems like it was kind of silly to do because you ended up with an equation, not a number. But basically what that means is if you wanted to find the area under the cosine curve from 0 to, I don't know, pi by 3, you would just plug pi by 3 in right down here and you would have your answer. Okay, what we just did in the last 2 examples was we were evaluating something called a definite integral. It's called a definite integral because there was an interval given. Told you where to begin and where to end. An indefinite integral is one where a no interval is given. So it's just basically asking you to find the area under the curve as an equation rather than a number. A definite integral, again, will have an a and a b value. It will be a numerical answer, and it represents the area from a to b. An indefinite integral will not have an a or b. The answer is a family of functions, remember, plus c, what we include there, and this is representing a general antiderivative. Here's your little cheat sheet, your table of values. You can use this to refer back to as we go through the next couple of examples. So I'm going to use a couple properties that were introduced in the last lesson. And the first property allows us in an indefinite integral or a definite integral to break up any sum or difference. So I'm going to do that. And I also am allowed to take any coefficient values and move them to the front of the integral. And that allows me to focus on just the variables or the trig expressions in this case. Okay, next I'm going to start taking the antiderivative. So now that the 10 is outside of the integral, the antiderivative will only be for this part of the problem. So remember, antiderivative is add 1 to the power, divide by the power. So this would be x to the 5th divided by 5. And then we will multiply that answer by 10. Okay, same thing over here. Antiderivative for secant squared x is equal to tangent of x. And then we will multiply that tangent of x by the 2 that was moved to the outside. Don't forget plus c. And then just simplify wherever possible. 10 divided by the 5 out here is really just 2. So 2x to the 5th minus 2 tan x plus c would be your general antiderivative, or we would call this an indefinite integral. Okay, this next example is in a definite integral because there are a and b values given. I'm going to go ahead and apply properties to this first. So I'm going to take the 6 out, and I'm also separating into 2 separate integrals so I can look at one thing at a time here. Okay, so let's start with an antiderivative for x to the 3rd. So x to the 3rd, add 1 to the power, divide by that power. And we will be plugging 0 and 3 into that. For x, it would be x squared divided by 2. Plug 0 and 3 into that as well. And now we need to maybe simplify first, and then we can evaluate. So this is going to be 1/4 x to the 4th minus 3x squared. And we are evaluating this whole thing from 0 to 3. You'll notice I decided to put them back to the terms back together just to make it a little bit easier to plug the numbers in. It's totally a preference thing. You don't have to put it back together in one big group. You can keep it split apart like I had up there. Okay, plug in 3. So I'm going to plug 3 in everywhere that I see an x. And then I'm going to subtract, and I'm going to plug in 0 everywhere I see an x. Okay, and then simplify is basically the last step. So 3 to the 4th is 81, so this would be 81 over 4 minus 27. 1/4 times 0 to the 4th, that's 0, and then we have another 0. So our answer is 81, go down here, 81 over 4 minus 27 is equal to negative 27 over 4. So your total net area is negative 27 over 4. All right, one more of these. This one has lots of constant values, coefficient values at the beginning, so you may want to apply some properties to break that up. So I'm just kind of moving the coefficient values out, including the 3 on this last integral. Actually, I think on this fraction here at the end, I'm going to flip this around, because if I do that, I think you're going to recognize the antiderivative for that one. All right, now we need to antiderive. So antiderivative for x to the third would be 2x to the fourth over 4, and then you have that, the 2 just drops down. The antiderivative for x would be x squared over 2. And then, I don't know if anybody caught this or not, but the antiderivative for 1 over 1 plus x squared, that's a table. It's in your little cheat sheet over here. All the way at the bottom, I think. It's inverse tangent. You may have seen one like that the other day. And all of these are being evaluated from 0 to 2. Okay? At this point in time, you may want to clean it up a little bit and call this 1/2 x to the fourth minus 3x squared plus 3 inverse tan of x. Okay? Now you can begin what we call the evaluation process, and that is plugging in the a and the b values. Remember, you always plug in your b value first. So there's what it looks like with the b value plugged in, and I like to group this together so I don't get anything mixed up. And then I'm going to plug in the value of 0. Okay, and then you just kind of work through simplifying all of this stuff. So 2 to the fourth is 16 times a half, that would be 8, minus 12 plus inverse tangent of 2. That's not a unit circle value, so I'm just going to leave it as inverse tangent of 2 and then keep moving. I would have a 0, another 0, and then inverse tangent of 0 would be like asking when tangent is 0, and that is also at 0 times by 3, and it's still a 0. So our answer would be equal to -4 plus 3 inverse tangent of 2. And if you wanted an answer that's more specific, you would have to get a calculator. And so that's going to give you -0.678. It says interpret the result in terms of areas. That just means that when you look at your answer, do you understand that if it's negative, that means the majority of the graph is under the x-axis because of the negative solution. All right, guys, last thing, and then we're going to touch on a couple things that you may see in the Delta Math assignment. So I want you to point out something super, super important to you. For antiderivatives and indefinite integrals, you cannot do product rule, quotient rule, or chain rule. You must look for ways to turn things into forms that you know how to deal with. There is no such thing as product rule, quotient rule, and chain rule for antiderivatives, okay? At least not that you know of. There's a little side note down here stating that. So it says, technically speaking, there is a product rule for antiderivatives, but it's something you would do in Calc AB. And also there is something for chain rule, but we haven't learned that yet either, okay? Moral of the story is, when you get a big old mess like this, your job before you try to take an antiderivative is to find a way to simplify the expression, okay? Now, in this particular problem, the easiest solution, I think, is you can break this into separate fractions because you only have a single denominator, okay? You are allowed to do this. Once you break it into separate fractions, you're then going to simplify each fraction. So like 2t squared over t squared, that would just be 2. This I can do like exponent rules if I wanted to, or I could just cross out the t squareds, and that would make this t to the 1/2. And then here at the end, maybe we'll write that as t to the -2nd power. Okay, now you may differentiate. So the antiderivative of 2, that would be 2t. By the way, we have to use the letter t because it says to take the antiderivative with respect to t. Next part, you're going to add 1 to your power, so that's going to make it 3/2. Divide by the power, which is 3/2. And then same thing here. Add 1 to the power, it becomes a -1. Divide by the power, which is -1. Okay, I think we need to clean this up before we try to plug anything into it. When you're dividing by 3/2, by the way, that's the same as multiplying by 2/3. So maybe just move that out. And then this would end up being plus 1 over t if we rewrote all of that. All right, let's plug everything in now. So now we have 2 times, we're plugging in 9 first. 2 times 9 plus 2/3. Maybe I'll rewrite this even as well, because this would be the square root of 9 to the 3rd power plus 1 over 9. Okay, minus, now we go back through and we plug in 1. All right, simplify. So 18 plus, let's see, square root of 9 is 3. 3 to the 3rd is 27. 27 times 2/3 would be 18. I'm distributing this negative as I go, by the way. So 2 times 1 is 2, but this would be a -2. Minus square root of 1 is 1 times 2/3, and then minus 1. Simplify all this stuff down, and you get 36, 34, 33 for the whole numbers. Minus, this would be equal to 5/9. And then we'll do one more step, and that would give you 292/9 as your area. Okay, last 2 examples. So application questions. This is just a PSA reminder, if you will, that when you're dealing with real world examples, if you have something that represents a derivative and you want to go backwards to the original function, you will have to take an antiderivative to do that. Okay? Exhibit A, you have a velocity. You want to go backwards to find the position. Okay? Velocity is the first derivative of position, so I need to take an antiderivative to go backwards to the position function. Now this problem says velocity is 4 sine of 4t. If the particle is at the position x equals -4 at time 0, what is the position of the particle at time 3 pi by 8? So step 1, guys, is going to be antiderive. Okay, remember this is equal to the position function. So antiderivative, let's start with sine. Antiderivative of sine is going to be negative cosine. And now we have something that we haven't ever had to deal with, because we have a baby. Let me just make this -4. Okay. This function, this sine function up here has a baby, has 4t as the baby. You know how normally we multiply by derivative of baby? Well, since we are doing an antiderivative, we won't multiply by the derivative of the baby, we will divide by the derivative of the baby, which is 4. So your antiderivative here is negative cos, because the 4's here and here would cancel, negative cos of 4t plus c. Okay, that's step 1. Step 2, you are going to take this value and this value and you are going to plug them into the function. Actually, I'm going to change this s of t to x. Sometimes that it's called x of t, meaning like the x value is the particle's position. I'm going to go to the right, and I'm going to plug in -4 for the x of t, and 0 everywhere I see a t, and that's like our initial condition, so that's going to help us find the value of c. So we need to do negative cos of 0. What is negative cos? Let's see. What is cos of 0? Cos of 0 is 1, so this would be -1 plus c. That means that c would be equal to -3 if you add 1 over. The third step is going to be to rewrite that equation with the c value plugged in. So that's what it would look like. And then you can do the fourth step, which is to apply the new function, apply the time value of 3 pi by 8, and solve. Okay, so we're going to have negative cosine 4 times 3 pi by 8 would be 3 pi over 2. And then you need to practice unit circle stuff because it's coming back here. Cos of 3 pi over 2 is 0. So this would be 0 minus 3, which is equal to -3. Let me do one more of those with you. So same exact type of question here. Start with your velocity function, and you're going to find the position by taking the antiderivative. Okay, so antiderivative of cos, start with that, that's sine. Okay, you have a 4/3 in the front that you will still have. You also have a baby here. 1/3 t is a baby inside the cosine function. So normally we multiply by the derivative of baby, but since we're doing an antiderivative, we will divide by the derivative of baby. And we're going to clean this up. So kind of doing an outer inner situation over here would give me 12 over 3, which is equal to 4. Don't forget your plus c. So that's your first step. Your next step is to take the initial condition and plug those in to find c. So remember, x is what the equation is equal to. And this time we're plugging in 3 pi. 1/3 times 3 pi would just be pi. So we need to say sine of pi is 0. So that means that c is equal to -4. And we can go back to the equation we had written here for position and plug -4 in for the value of c. So you have an equation that finds the position of the function at any given time. Then you're going to evaluate the position of the function at the time 9 pi over 4. So you'll be plugging in 9 pi over 4 for t. Okay, and then simplify in the parentheses. So 1/3 times 9, that's going to make this 3 pi over 4. Sine of 3 pi over 4 is radical 2 over 2. And we can keep simplifying. This would equal 2 radical 2 minus 4. Now, I don't know if Delta Math wants a decimal or a simplified answer, but from this point, you would either type in this solution or make it a decimal and type that in. Okay, that is it. So go ahead and give your Delta Math a try. let me know if you have any questions.